most typically when we encounter data, we have the specific value for the observation in front of us. So if you have a data variable of height, or if you have a variable of height, you have the specific height of each observation there. So you have somebody that is 65 inches tall and another person that is 67, and you have a specific value for them. Now, that is not always the case. Sometimes we come across grouped data, and cases where this might be is, for instance, if you, and you've filled out these surveys, I'm sure of it, where you select a range in which you fall. You may fill out a survey sometime and it asks you to say, what's your GPA, or maybe you filled out what your high school GPA was, and there were different bins, right? So you might have clicked the button that said 2.5 to 2.99, and then there was another bin for 3.0 to 3.49 or something like that, in a series of bins, and that should look somewhat familiar, because in chapter 2 we actually took we took data and put it into bins. Here, in this sense, sometimes we have data that comes to us in kind of bins already, and that we don't have the specific value. We have what bin the data might be in. And so we can do many of our same techniques when we have grouped data like this, but we do have to alter kind of our processes a little bit. So we're going to look at a couple examples of that, and that is how do we take the mean of grouped data, and then also the standard deviation of grouped data. And those are going to go hand in hand, again, because remember, standard deviation, we use the mean in there, and we'll do the same thing here. We'll use the grouped mean, or the mean of the group data, to calculate the standard deviation of the group data as well. So again, this is going to have a mirror if we're in samples or population. We're going to work with the sample data here, and so something like the mean, we'd refer to it as x bar, and that mean we're still going to sum up, but we want to it's not going to just be over x here. It's going to be, we're going to look at the frequency and the midpoint. And we're going to divide by n. Again, we're in the sample world, so that's a lowercase n. Now, let's work with, let's see what we come up with that GPA example. So let's say we had 10 students, and we were curious about their GPA, or we had gotten data for it, but the way we had gotten it was to ask, was your high school GPA 2.0 to 2.49, and we'll just leave it as kind of actually, for the sake, and again, this is going to have a little bit of we would have to say, I'll do 2.0 to, well, now it kind of looks like greater than. Bear with me here as I make sure we're being clear. So that's even less clear. So up to 2.5. So anything less than 2.5, and then so it might have looked like, oh, fill in the bubble if that's the one you have, or if you have 2.5 to less than 3, 3.0 to less than 3.5. Let's assume that, I know probably with AP classes or whatnot, you can get greater than 4, but let's say it finishes at 4. So actually, that would be not up to, but, well, we could just do less than or equal to. So maybe those were the 4 options. I guess you'd probably have an option for less than 2, but let's say these were the 4 options, and we got the following results out of our 10 students. So we had 2 let's say 3, 2. What does that leave me? That well, let's do 1 and 4. Okay, so that should be 10 students. So we have 10 students, and they each selected one of these options. And here's what we had. Now, if we wanted to think about what's the average GPA across these students, we can still calculate that, even though we don't have the specifics. Now, of course, what we end up with here may not be exactly their average GPA across the 10 students, because each of these is just an estimate of the actual value. Okay, because if you had a GPA of 2.4, we're not going to use 2.4 here. We're going to use some measure of you being between 2 and 2.5. And what we're going to use is the midpoint. So we're going to assume that both of the, one way to think about it is that we're having both of these people have a GPA of 2.5 or 2.25. Okay, we're not actually assuming that they, well, we know that that's not true, but what we are saying is on average they're probably spread out across this range. And so let's take the midpoint and have them both count as that. So how do we go about calculating this? I'm just going to switch colors so it stands out a little bit more. The way we do this is we're going to follow this formula up above. So what we want is the so we're gonna rely on the frequencies, and so the frequency, so this is going to build out to 2 times what's the midpoint. So we're going to use the midpoint of each group. So this is 2 times 2.25 plus 3 times 2.75. I'm going to need to kind of continue on the next line, plus, supposed to be a plus, plus 1 times 3.25, and then plus 4 times 3.75. I was not kind to myself as far as the math goes, but so that's the numerator here. The denominator is going to be divided by, so not 4, almost tricked myself, divided by n. And again, we took a sample of 10 people, and so we have 10. Okay, so this should feel familiar. This is essentially, or it's very similar to the weighted means that we took before. Okay, in the sense that we are, we're using the 2, the 3, the 1, and the 4 as the weight on each of these. The big change here is that we're taking that midpoint to kind of estimate each of the groups. So let's just finish out this math. So that's 4.5. So 2 times 2.25 plus, what is that? 6, 7. So 3 times 2.75. So 8.25. Plus 3.25 plus 4. Let's see, 4 times 3.75 is 15. Okay, and that's divided by 10. So when we add all that together, bear with me as I double check this math. So we get 31 divided by 10, or our estimated average here is 3.1. Okay, so x bar equal to 3.1, and that's our best guess for the average of these 10 students. Now we will then go through the same process, or use the same kind of idea, relying on the midpoint. We can go ahead and calculate the standard deviation. So let me try to grab this data. And so just like we do with a normal standard deviation, we're going to rely on the sample calculation, or the sample formula. So that's S is equal to right, the square root. Inside of this, we're calculating the variance. We're still going to sum. We're going to look at the deviations. Remember, the sample we have n minus 1. But up here in the numerator, instead of, again, the normal deviations, we're going to look at, again, a grouped, or we're going to kind of use that weighted concept. And then we're going to look at how far the midpoint is of each group compared to the mean. That's squared. All that's within the square root. Okay, so again, what we're taking out is kind of the specific values of x, and we're relying on the midpoint of the group. So let's walk through this example. Trying to think of the organization here. So what we have is, some sense, let's look at our midpoint as 2.25. Right, our 4 groups are 2.25, 2.75, 3.25, and 3.75. Right, and then m minus x bar being the deviation from the mean, where the mean is, again, what did we calculate that as? 3.1. Let me just remind ourselves. X bar is 3.1. Okay, and so what we have here is 2.25 minus 3.1, or 0.85, negative 0.85. Okay, and then we can do the same for the rest, and we'll eventually square these. So 0.85 squared is 0.7225. Okay, we get this next one is minus 0.35, and that comes out squared as 0.1125. Next we have positive 0.15, which becomes 0.0225. Okay, and then lastly, what is this? 0.65. And that becomes 0.4225. Okay, so we have the squared deviations. Whoops, I did not mean to cross that out. We have the squared deviations. Same, or almost the same process, but remember, we have to bring with it, when we sum these up, we want to bring with it the frequency, right? Because there's not just one 2.25. There are 2 of them in which we need to treat as 2.25. So we could have listed them all out. We could have had 10 values listed here, but instead we're just doing it 4 times. But we need to bring with it the f, the frequency. Okay, so what we're really going to sum is 2 times 0.7225 and 3 times 0.1125 and 1 times 0.0225, and then lastly 4 times 0.4225. Okay, so we sum those up, and so we get, it's just 0.5, and that is going to be the numerator that we've calculated before. And then lastly, all we need to do is take the average of those. Okay, so there's a distinct possibility I made a mistake, but what I get for a total here is 3.49. Seems a bit high. Well, everything kind of checks out here. So we'll go with that. And if I made a mistake, then you can let me know or just correct it yourself. So we have a total of the, what do we have here? We have well, this is not the sum. The bottom there is the sum. So we have f times m minus x bar squared. And then down here we have the sum of that. Okay, lastly, we need to divide by n minus 1. Okay, so we're jumping all over the place here. But 3.49 divided by 9, right? N minus 1 is 9. And that's going to give us, I guess it's 3.495, technically. Divided by 9, we get 0.3883, and that is our variance. And then lastly, the very last step is to take the square root of that, which means we're below 1, so that's going to get bigger, right? And so our standard deviation is 0.623. Okay, so sigma 0.623. Okay, so both the mean, right? The mean, which we found as 3.1, and the standard deviation. So I have a little mistake here. This is not sigma. This is S. Okay, so we are in the sample world, so we need to make sure that we're aware of that this is an estimate of those, the kind of actual values there. So, yeah, so nothing too earth-shatteringly different when we go ahead and use the group data. And again, most of the time you see data in the specific values there, but it's not that uncommon, you know. And again, as you've seen filling out surveys, sometimes you are asked kind of those bracket questions, or what's your income last year? Was it 10 to 20,000 or 20 to 30,000, and so on. So again, not that rare. So good to be aware of the ability to do this. This won't come up all that often the rest of the way. You know, a lot of times we'll rely kind of on having nice clean data where we know what the values are, but we may see it from time to time.